Okay, well, I think we might as well get going. So yeah, welcome everybody here to the PhD defense of John Bartolotta. It's been a tremendous privilege to have him working in our theoretical research group for a number of years now. He's covered a whole lot of topics in quantum physics, ranging from, let's say, quantum information science, ultra cold gases, manipulating atoms and molecules with laser light, and cooling and trapping, and understanding the process of lowering entropy and bringing things from the classical world into the quantum world. So it's been a whole variety of topics, and tremendous privilege to have him and to have all the advice he's given to various students along the way as well. So I'm going to just hand it over to you, John, and let's start with your talk. And the general format for the exam is going to be, it's going to give a talk around three quarters of an hour or so, during which you can ask questions, but we'll try to keep the questions to clarifying kind. Then we'll ask general questions after the exam, and then we'll go to a sort of a closed session with just John and the committee itself, and we get to grill him for a while, and then we can move everybody into a breakout room, I think, at that point, if that works technically, and then come back and hopefully open some virtual bubbly. Let's move it on to you, John. Kick it off.
Great. Are we rolling, Mary?
We are rolling. You mean the camera's
rolling?
rolling? Camera's rolling.
Yep. Just making sure everything's all set. Thanks, Mary, for the introduction, and thanks to everyone for joining. Let's make sure this is going. There we go. All right, the name of my thesis and of my talk is Advances in Laser Slowing, Cooling, and Trapping Using Narrow Line-Width Transitions. I did this research over the last 4.5 years at JILA and the University of Colorado Boulder under the advisement of Murray Holland. So to start, a lot of the projects that I'll be discussing today has to do with moving atoms and molecules around by using light. So I wanted to give a few perhaps more familiar examples of how light can push matter around. Many of us had the pleasure of seeing the comet Neowise fly past Earth just about a year ago to the day. And if you were to look up at the sky and see the comet, you would notice that there was this trail, this tail of the comet that's kind of flying as the comet moves around the Earth. And if you were to follow that tail on the other side, kind of down into the left in this picture, you would find that it points towards the sun. And the reason that happens is because different things on the comet become heated and vaporized on the near the surface of the comet because it's near the sun. And then as that happens, the light from the sun starts pushing some of that matter away from it. So that's why you actually see the trail going against where the sun actually is. Another example is what's called a solar sail. And what this is a way for spacecraft to move around the solar system and generally anywhere as far as they can get in the universe. And the way these things work is it's essentially just a big metal plate that you face towards the sun. And just like a sailboat catching the wind, this sail actually catches the light from the sun. And this will allow the spacecraft to move and be blown away from the sun so it can move around. Now, something that's a little bit closer to what I'll talk about today is what's shown on the bottom here, where I take a laser and I essentially shine some light on it, on an molecule next to the laser. And if I turn on my laser, then I'll find that the atom will start moving away. Now, to understand why that happens, we have to look a little bit closer into this laser field. And what we find is that the light is actually made up of individual little packets of energy called photons. And these photons have an energy which is given by this expression here, where h bar is a constant and omega is the frequency of the light. And they also have momentum, which is given by this expression h bar k, where k is related to the wavelength of the light. So in order to understand exactly how this photon is going to affect the atom as it absorbs the photon, we have to look a little bit deeper into what the atom is doing. So the atom has electrons that are whizzing around, as you can see in this picture here, and these electrons can have different energies. And so let me go ahead and focus on two specific energy states that this electron can possibly be in. And I'll call this lower state the ground state, and this upper state, which has more energy, the excited state. So so these two states are separated in energy, like I said, and this separation in energy is related to what's called a transition frequency. between these two states. And if that transition frequency matches the frequency of the photons that are coming out of the laser light, then what will happen is that electron will actually absorb that photon and it will be transferred to this excited state. And because the photon also had momentum, the atom will start moving. So that's just to give you a general picture as to why we can expect the atoms and molecules to start moving. Now we can actually use this process to make a gas of atoms and molecules very, very cold. And to demonstrate how that works for you, I'm going to describe a very common laser cooling technique called Doppler cooling. This is the most commonly implemented laser cooling technique. It's been around for decades. It works well, it's efficient. And the way that it works is the following. So I take my atom and I put it in between two lasers and I turn my laser on. And what will happen is elucidated by taking a look at this two-level energy diagram again. I'm going to label the frequency of this left laser with this arrow here, and the frequency of the right laser with this arrow here. And if you notice, the frequency or the length of these arrows is slightly shorter than the spacing between these two energy states. And what that means is that the laser is actually what we call red detuned. And we call it red detuned because our eyes perceive red light, which has a lower frequency, as being red. So because this atom is in between these two lasers and these two frequencies look the same, that means that the atom is stationary. It sees both the frequencies as being the exact same color. But now let's consider this, what happens if the atom starts moving, say, to the left. In that case, the frequency of this left laser actually gets shifted up a little bit, and the frequency of the right laser gets shifted down. And this is due to what's called the Doppler shift. And this is the same kind of Doppler shift you experience with sound when an ambulance comes by and it sounds high-pitched when it comes towards you and low-pitched when it goes away. And because in this case, this left laser is closer to this energy, we call it to be on resonance with the atom, and the atom will absorb photons from that laser. And because those photons have momentum, it will serve to slow this atom down. Now, the same argument can be made if this atom is moving to the right. In this case, the laser to the right is closer to resonance, and now the atom will absorb photons from that laser instead. So no matter which way it's moving, these lasers will serve to slow down the atom by the absorption of photons by the atom. Okay, so how does this actually work? In principle, in order to slow an atom down, you have to bombard it with many photons. And I told you before that in order to absorb a photon, the electron in the atom has to move from the ground state to the excited state. So how does it get back to the ground state to absorb more photons to slow down? And the way that typically happens is what's called spontaneous emission, or sometimes I'll call it spontaneous decay. And this is a natural phenomenon where higher energy states have a tendency to relax down to lower states. And what that means is that this atom will eventually emit a photon if it were in the excited state and go back to the ground state after some time. So why does that help us with the cooling? Well, let's go ahead and look at our laser and our atom again. The absorption that I talked about just a moment ago on the previous slide will serve to slow down the atom. And then afterwards, it will move back to the ground state by emitting a spontaneous photon. And these spontaneous photons can actually be emitted in a random direction. So as I keep absorbing, slowing photons and emitting these spontaneous photons, what I see is I actually get a slowing from the laser photon. And on average, I get no net force from the spontaneous photons since they're going in a random direction. And the net result of this process is that we get very cold atoms. For typical parameters, we can get temperatures all the way down to the microkelvin regime, which is about 1 billion times colder than the room that you're sitting in right now. And this actually happens very quickly. We can cool atoms down in the order of milliseconds. So that's 1,000th of a second. Moreover, this process can be used not just to make the atoms very cold, but we can also localize them in a very specific point in space, and that's called trapping. And I'll also discuss that more later in the talk. So why is this kind of laser cooling and slowing and just generally controlling process useful for us? The reason that it's useful is because we can have ultimate control over the dynamics of atoms and molecules. And what that means is that we can do studies of fundamental physics. For example, we can study a phase of matter that doesn't exist at regular room temperature and pressure called the Bose-Einstein condensate. And we can make those things, we can realize them in the laboratory by shining some laser light onto some atoms and then watching them spontaneously emit photons until they become super cold and all kind of wind up in the same location. Another thing that we can do is, since we have such good control over the atoms and molecules, is we can actually orient them in what's called an optical lattice. which you can see it, here's a diagrammatic representation of that, where we have different, in this case, molecules at different sites of this lattice. And we can cause them to interact with each other. We can zap them with laser light and individually and make them do special things. And we can just generally understand exactly how they're interacting with each other. Moreover, we can actually realize something called quantum simulation. And what that means is that we take this type of system that we have good control over, and we simulate much more complicated physics by tuning the interactions correctly. On a related note, and probably something you've heard of recently, is another thing that we can do with this control called quantum computing. And that allows us to actually take our atoms and molecules and manipulate them in such a way that we can do computations with them in the same way that we do computations with our regular computers. And this here is a picture or a diagram of a particular quantum computer over at IonQ in Maryland, where they make a so-called trapped ion quantum computer. And they trap a bunch of atoms very close at the center here, and they manipulate them with electromagnetic fields and light and really do computations like a computer does. Okay, so let's go back to what was going on with Doppler cooling. I made it sound great, right? We can get really cold atoms, but what are some of the limitations of Doppler cooling? One of the biggest limitations is this potential decay to other states. And what I mean by that is, although the spontaneous emission is integral to the realization of Doppler cooling, in reality, the electrons may be able to go to many other different states in the atom. And if they spontaneously emit to some different state other than this ground state I called G, then they may not talk to the laser anymore, and I might lose them and I can't cool them anymore. So that eventually leads to atomic loss. Another problem that arises is that we have to essentially wait for that spontaneous emission to occur every single time so we can hit the atom with more slowing laser light. So if this spontaneous emission takes a very long time, then we will not be able to apply very large forces since we have to wait so long. And another way to say this is called it's a weak or a narrow transition, where that spontaneous emission rate is very small. So in summary, the limitations or the Doppler cooling is limited to simple atoms with very strong transitions. So we can ask the question, can we do better than this? Is there some protocol for laser cooling that has a reduced reliance on spontaneous emission, where I can kind of take my electron and move it between these two states many times and not have to worry about spontaneous emission every single time? And if there were a method that we can do that with, then we would have less atomic loss. We could maybe apply larger forces. And it turns out that there actually is a way to do that. It was discovered at JILA a few years ago, and it is called swap cooling. Here's a nice fancy picture from the press. And essentially what this allows us to do is not have as many spontaneous emissions occur during the cooling process, and thereby giving us more coherent control of the laser cooling dynamics. And I'll go into a lot more detail later. Let me present some of the main results that I'm going to share in these different sections in my talk. First, I'm going to elaborate on the swap cooling from a theoretical perspective and also from an experimental perspective, and I will call that section cooling. And then next, just like we saw how Doppler cooling, or I mentioned how Doppler cooling can be used to trap, we will do the same thing with swap cooling and show how you can actually realize the so-called magneto-optical trap. And this picture over here is not from the swap type of magneto-optical trap. This is a picture from a regular or a conventional magneto-optical trap. But I just want to show you the difference between cooling and trapping. Notice where I'm putting my laser pointer here that the atoms are at a very specific point in space. That's what I mean by trapping. Cold just means they're not moving very quickly, whereas trapping means they're in a very specific spot. After that, after we've extended the swap, about how we can make the swap process even faster. And we'll apply that in the context of particle slowing. Now I want to clarify something. I say speed up swap, and then I say slowing. What I mean by that is that the goal of that section will be to slow down atoms, but we want to slow them down in a small amount of time. And that's what I mean about speeding up the slowing process. So hopefully that's a little clearer. And then the last thing I'm going to talk about is to understand how the laser light that we use for these types of processes can possibly be affected by the interaction with the atoms and the molecules. And I'll call that section entropy removal. Okay, so let's jump right into the cooling section. So I want to introduce a humbling quote from Matthew Norcha, who was a graduate student at JILA when swap cooling was first realized. And he says that basically I pressed a button on the function generator. So with this relatively easy thing, we discovered a whole new interesting part of laser cooling physics and led to a lot of the results I'm about to show. Okay, so how does swap cooling look? Let's go ahead and do our same picture as Doppler cooling, where we have our two lasers and our atom, and we also have this two-level system again. What we're going to do now is, instead of keeping our laser detuning red detune, we're going to allow the laser frequency to go from this red detuning and go past resonance and into blue detuning over and over again in this so-called sawtooth waveform. And if I can bring your attention to this frequency diagram here, just in case that's not clear, notice I'll show you a couple snapshots in time of how this arrow goes up and up, hits resonance, goes up again, and then immediately jumps back down for the next sweep. And that happens over and over again. And the fact that we're doing the sawtooth ramp explains the first half of our acronym. It's sawtooth wave. And the second part is called adiabatic passage. And now what the adiabatic passage part means is that we essentially need to make what I, for lack of a better word, will call a gentle ramp. And what I mean by that is that this ramp is not too steep. Okay, so what do I mean by not too steep? Let me introduce something called the Rabi frequency, which characterizes the interaction between the atom and the laser. And let me also introduce this parameter alpha that describes the slope of the sawtooth wave. So in order for the ramp to be gentle, then I need to be in the regime where this Rabi frequency squared is much bigger than the slope of the sawtooth wave. That means, for instance, if I have a very high intensity laser, that I can actually make my ramp a little bit steeper and it will still be considered gentle. But nevertheless, this inequality needs to be held in order for this process to work. So let's go a little bit deeper in understanding how the swap process actually works. And in a nutshell, it's laser absorption and emission. So I'm not only going to absorb a photon from the laser, but I'm also going to emit another photon into the laser instead of doing the spontaneous emission process that I mentioned for Doppler cooling. So let's look at our two-level system again. And let me show you what happens over a single sweep, where the electron, we'll say, starts in this ground state. And now I start sweeping my laser frequency. Eventually, at some point in the first half of the sweep, the electron will be transferred up to the excited state upon absorption of a photon. And then sometime in the second half of the sweep, it will interact with the other laser, and the electron will move back down to the ground state. And what actually dictates the times that this happens is the Doppler shift, the same thing that caused frequencies to change back in Doppler cooling. And what happens in this case is that we actually get two kicks against the motion, whereas before we only had one kick against the motion from the laser. Now, spontaneous emission is also essential in this laser cooling process. So let me show you one of the ways that it comes up. Let's say that I did the same description I said a moment ago, but I started the electron in the excited state instead. Then it would still undergo these two laser processes and would wind up back in the excited state. But because it started in the excited state first, what would actually happen is that it speeds up instead of slows down. So spontaneous emission will allow us to actually start each sweep in the ground state if we set our parameters correctly. An obvious question you can ask about swap cooling is, how cold can swap cooling make something? So to address that question, let's take this idealized scenario where I allow the spontaneous emission rate to go to 0. So there's essentially no chance for spontaneous emission. And I make my ramp very, very gentle. So I'm very adiabatic. These transfers are going to happen with very high fidelity. And then after a sweep, I'm going to wait a very long time in case there really was going to be a spontaneous emission. It will happen at the end of that ramp and then before the next one starts. Then what happens is shown in this plot here. This is a simulation that I made where you can see that the kinetic energy of a particle, which starts relatively high, decreases as I do more and more sweeps. And towards the end here, the kinetic energy kind of equilibrates and winds up staying at a more or less equal value. So let's zoom in a little bit and see what it looks like in there. Okay, so now, since the kinetic energy of the system has equilibrated, I can assign a temperature to describe how hot or cold the system is. And we find that it actually hovers around what's called the recoil limit, or the 1D recoil temperature. And this temperature is so cold that each atom on average has a kinetic energy that corresponds to just one photon absorption. And for some narrow line with transition parameters, this would mean that we can go lower than microkelvin temperatures into the nanokelvin regime and approach what's called the ultra cold physics regime. Now, I also wanted to show an experimental realization of a similar process. So this right here is not the ideal swap anymore. It's actually in a real atom called strontium-88, and it's on the singlet S0 to triplet P1 narrow line with transition. And same thing that we saw in the simulation, it starts with a relatively high temperature and it decreases as the cooling time goes on, and it equilibrates to a lower temperature. So this really does work in the experimental realm as well. The next question that we want to answer is whether or not the swap process is more efficient than the Doppler process. And what I mean by that is, do I need to actually secretly have lots of spontaneous emissions in this process to ultimately make it work? Or does it actually have fewer spontaneous photons than Doppler and would thereby be more useful in some circumstances? Well, to answer that question, I want to show the simulation result. And what this shows is a similar process as before, where I initialize an atom with some relatively high kinetic energy. And now I allow it to evolve under the swap process, which is this purple curve, and then separately under the Doppler process, which is this green curve. And we find that the kinetic energy is reduced with fewer spontaneous emissions or fewer scattered photons in the swap case than the Doppler case. So according to this metric, swap really is a more efficient protocol. Let me summarize what I've discussed so far for swap cooling. Basically, it works from a theoretical and an experimental perspective. We can get cold temperatures very fast, very easily. If you can do Doppler cooling, you can almost certainly do swap cooling. And because of the more efficient nature of swap cooling, we might be able to actually apply this to systems that are more complicated, where those spontaneous emissions can really cause the cooling process to stop. The next thing I want to discuss is how we can take the swap cooling process and extend it to apply a trapping force in addition to a cooling force. Before I do that, I want to explain a more the conventional type of magneto-optical trap that people typically use in order to achieve cooling and trapping. And essentially, in that case, we take our Doppler cooling setup and we add a magnetic trap. And what I mean by that is that one way to get this magnetic trap is to take coils and place them above and below our atom and run some current through those coils. And what will happen is that inside this region over here, as the atom moves around, it will experience a magnetic field that depends on space. Now, in addition to doing that, we also need to consider not a two-level system, but a three-level system with one ground state and two excited states that I'll label plus and minus, and that will become clear in just a moment. So here's a simplified picture of the MOT. Now I have my coil still, and I've replaced the lasers with these squiggly lines and these two variables called sigma plus and sigma minus. And this has to do with the polarization of the light, which will allow us to do different transitions in our system. So more specifically, for example, for the sigma minus beam, the atom will it will transition between this ground state and the minus state specifically. And for the sigma plus, it will do the same thing with this transition right here. Well, now what happens if I put this particle inside my trap is that the two excited states will experience what's called a Zeeman shift that depends linearly on how far away I am from the center of the trap. I'm allowing this particle to only move kind of along a rail. It's a 1D kind of scenario. And the ground state doesn't change, but the excited states will get split, and the plus state has a higher energy and the minus state has a lower energy in the region where the magnetic field is positive, and then vice versa. How does this actually arise in a trapping force? Now let me try to explain that now. This is a relatively complicated picture. But in order to make a MOT work, again, we want cooling and trapping from this thing. In order to achieve the cooling, we do the same thing as in the Doppler cooling case, where we take our laser and we red detune it from the transition. So here's my laser frequency by this horizontal line. Now let's see what happens if I take my particle and I move it to the right, so it's on the right side of the trap. In that case, the two excited states will experience that Zeeman shift I mentioned. And notice that it's the minus state that is closer to resonance with the laser than the plus state. What that means is that the atom is more likely to absorb from the sigma minus beam. And because the sigma minus beam is coming from the right and moving left, then when the atom absorbs a photon from it, it will get a kick towards the center of the trap, thereby yielding the trapping force that I was talking about. Just like in Doppler cooling, this particle will quickly emit a spontaneous photon, and it can undergo this trapping force many times. And what will happen is essentially it will be localized close to the center of the trap and kind of move left and right, but stay focused on the center. So the next question is, how can we replace the Doppler cooling process in this MOT with the swap process? The setup is very similar to a conventional MOT. We still have the same internal structure, and we still have the same experimental setup. But now, instead of having a red detuned laser, we're going to do the sawtooth ramp below to above the transition frequency. So going up and down kind of like this. And moreover, in order to make the dynamics work, in the second half of each sweep, we have to switch the polarizations of our lasers. So now sigma plus is over on the right. And we also have to switch the directions that the currents are flowing in coils. And that effectively changes the direction of the magnetic field inside of our trap. Now, why does that have to happen? How exactly does this process work? Let me try to explain that now. In the first half, very similarly to the Doppler, the regular MOT case, I will absorb a photon and move to this minus state if I'm on the right side of the trap. But now, in this swap MOT, in the second half of the sweep, I told you that we're going to switch the magnetic field direction. So now this minus state gets switched to the top, and the particle is sitting up here. And as I continue my ramp and hit resonance again, it will resonate with the sigma minus beam, which is now on the left because I switched the polarization. And that will cause the particle to undergo stimulated emission into that laser and get another kick towards the center of the trap. So this method gives us 2 kicks towards the center of the trap instead of 1, and it required 0 spontaneous emissions. Now, to show you that this actually, of course, we have these competing processes. We have cooling trying to go on, we have trapping trying to go on. Let's see how they all come together. And the way to do that is to look at what's called the phase space of the system. And what this essentially means is to take a 2D plane and along this horizontal axis, plot the position of the particle at any time, and along the vertical axis, plot the momentum of the particle. And these results that I'm showing here are simulation results for a particular narrow line transition in yttrium monoxide. Now, I want to point out that there are a bunch of yellow dots that are kind of spread out as I'm circling them here. That is the initial, that's the initial scenario. I have many atoms, and they are, or many molecules in this case, spread out in my trap. And then what happens is evidenced by these green lines. So for some of these yellow dots, I've shown that they kind of spiral in time, and they wind up going right to the center of the trap. And where they end up finally, I've put in purple. So in the end, they become cold and confined, and before they were hotter and more sparse. So we really do achieve cooling and trapping in the swap MOT from the simulation, and we actually undergo what's called phase space compression. Okay, same question as before. How cold is it and how trapped is it? So specifically what I'm going to show you now is to understand a little bit more about the distribution of the particles in this purple, this part in the center of the trap that are labeled in purple. So first, let's look at the momentum distribution. So this is the probability of each particle having a certain momentum. And we find that it's centered on 0, and it has a spread on the order of a few photon momenta. And what that means is that the temperature is pretty close to that 1D recoil temperature that I had mentioned in the idealized swap case. Now, in terms of the position distribution, where this is probability of being at a certain point in the trap as a function of position, we find this kind of funky looking distribution, which is actually the sum of 2 Gaussians. And the spread is on the order of tens of wavelengths. And what that means for this set of parameters is that the cloud size is smaller than a millimeter in extent, which is often smaller than many conventional MOT cloud sizes. So let me summarize what we talked about here. Swap can be used to cool and to trap, right? In order to get the trapping, we have to introduce the swap MOT, which is what I discussed in this last section. And we can get low temperatures as a small cloud size, very fast. And maybe with the same logic as before, we can apply this to situations where atoms and molecules, to more complicated atoms and molecules that we may have lost to spontaneous emission in the past. Next, I want to discuss how we take these types of protocols and we make them happen faster in time. And in order to do that, I'm going to consider a situation where I want to slow down a bunch of particles. And again, I want to clear up something. We are slowing particles down, but we want to slow them down quickly. That's what I mean by speeding up the slowing process. And in this scenario, I have some particles that may have some high mean velocity, and I essentially, by some method, want to somehow get them close to 0 velocity. And that's what I mean by slowing them down. Now, this is a slightly simpler situation than cooling because I only need a one-way force, right? If they're moving towards the right, I got to push them to the left and then stop them. And I don't have to worry about turning them around again like you have to do in cooling. Now, the way that this is realized in an experiment is you have some kind of source, maybe an oven, where particles are flying out with some kind of high temperature or high velocity, kind of like in this solid curve. And they move into this region where we're going to apply laser pulses to try to slow them down. And these laser pulses will have time-dependent frequencies, omega-1 and omega-2. The question we're trying to answer here is there a way that we can administer these frequencies that is better than the sawtooth wave that we did in the past? Can we optimize omega-1 and omega-2? And in order to do that, we apply what's called an adiabatic speedup protocol. To remind you what adiabatic passage means, it was this gentle ramp that I had discussed before. But now I want to apply a shortcut to adiabaticity. And there are many different types of shortcuts that have been brought up over the last few decades. And we specifically chose one called Lewis-Reisenfeld invariance. And what this particular slowing protocol allows us to, or speed up protocol allows us to do, is to inverse engineer the Hamiltonian that describes our system. And that will allow us to find new laser intensities and frequency schemes to achieve the same results that we would have gotten from swap, but in a much faster time. And the answer is we succeeded. We can go faster than swap. I've tried to show kind of what the new laser detuning distribution looks like. It's more, it's not linear anymore. And I've colored them red and blue because we have these pulses coming from the left and the right. So the red one is the right, the pulse coming from the right, and blue is coming from the left. So is this actually faster? Did this Lewis-Reisenfeld invariant give us a process that we can do transfer, but more quickly than the adiabatic processes? And so more specifically, consider if I want to have a particle be slowed down, I start it in the ground state with some momentum p, and I want to move it to the excited state with some slightly lower momentum by applying this laser pulse. Now, what we can do is we can look at these two states and we can map them to what's called a Bloch sphere, which is a useful representation to understand the path that the system takes in going from the ground state to the excited state. And I have three curves here on my Bloch sphere, and this blue super curvy one corresponds to the swap-like adiabatic case. As you can see, it takes a very long time, or takes a long path around this. And then this red curve is the shortcut path that we derived. And lastly, this yellow one is called a pi pulse path. And that was done by applying resonant light for a very specific amount of time. Now, why is the shortcut method arguably the best of these three? First of all, it is faster than the adiabatic path. That is what we wanted to do before. Secondly, it is more robust than the pi pulse path. Notice the pi pulse path is the fastest, but the pi pulse method suffers from sensitivities to small variations in the intensity of the light and the frequency of the light. So if we apply those same sensitivities to the shortcut case, we would wind up a lot closer to the excited state in general than we would by applying the pi pulse method. And that way we say that the shortcut is more robust. Now let's show that it actually slows down some atoms. So here's some simulations that I did. I want to keep that two-level picture in mind. And this right here is the probability of being in a certain momentum state. The blue curve is before the slowing process, so I initialize it at 100 photon momenta. And the yellow is the distribution after the slowing process. So specifically, this process was done from a so-called single momentum state, because I started all at 100 h/k. And also, this is specifically doing slowing where I turn off spontaneous emission, and it is not allowed to happen. And as you can see, with almost complete fidelity, I can bring my particle down to 0 momentum with no spontaneous emissions. Now let's go ahead and see what happens if, instead of initializing the particle with a single momentum, let's consider particles with a spread, or a Gaussian spread of momenta. And again, with no spontaneous emission, we see that a huge chunk of them get slowed down to 0 momentum. So it still works quite nicely. Next, let's turn on spontaneous emission, which is explicitly what we don't want to happen. And this is the result for the single momentum case. It gets brought down close to 0, but not quite all of the population gets there. And then for the Gaussian case, I still get a significant chunk that gets pushed down to 0 velocity, even when spontaneous emission is allowed to happen. So in all cases, we were able to slow our atoms down to near to 0 momentum. And in the cases with spontaneous emission, each particle emits about 1 spontaneous photon. And if we were to do an equivalent like Siemens slower Doppler-based mechanism, there would have been 100 spontaneous photons instead. And because we have more coherent control, if we have sufficiently high laser intensity, we can slow these down these particles down in the order of millimeters, or maybe possibly even smaller if you have a strong enough laser. So let me summarize what we talked about here. I showed that we can speed up this adiabatic passage process, and we actually show in a paper that we wrote on this that we can slow many different types of atoms and molecules. We apply it to calcium, strontium, barium monohydride, and also that same transition in yttrium monoxide, and show that we can actually get superior slowing with this process. And future work includes trying to apply this to laser cooling and trapping instead of slowing. I anticipate that this would be an easy extension, and also explicitly incorporating the spontaneous emission or dissipative effects into the shortcut protocol from the get-go, instead of hoping that it doesn't happen, to see if you can get better results. Let me move to my last project now, which I named entropy removal before. And it's a little bit more abstract of a concept. In the laser cooling process, what happened was that we essentially reduced the number of states that the atoms could populate. And what I mean pictorially is, here's a grid. Let's say that each little box is a specific state that a given particle could be in. By applying the laser cooling process, we cooled them down, and now they can occupy fewer states. Now, this is what is typically called entropy reduction by a physicist. And the question is, in this case, exactly how did that happen? Well, in the case of laser cooling, we know that spontaneous photons were flying out of our atoms. So maybe that entropy removal was done by the spontaneous photons. But there's also another degree of freedom in our problem, which are the laser photons. And typically we say that these laser photons, or that the laser itself is unperturbed from the interaction. But now we discovered a protocol where the spontaneous emission doesn't happen as much. So maybe it's important to think about what happens to these laser photons in that scenario. So our main questions in this are, is the laser field changed at all by the atom? Right, we have these absorptions and emissions. Is it the same state or not? And then secondly, can the laser field actually do this for a reduction of entropy and bring us to this lower populated state kind of situation that I mentioned? And the way that we're going to do that is by considering a simpler situation where we remove the atomic motion. So now we have an atom that's nailed down at some point in space, and we put it in what's called an optical cavity. And these two dark blue things are mirrors, and light is allowed to bounce back and forth in between them. And we're explicitly going to track the evolution of the light now. Before, like I said, the light was treated as a laser that was unperturbed. Now we're going to track each individual, the quantum mechanical degrees of freedom of the light. We are also going to simplify things and say that this cavity is lossless, so no light leaks out of these mirrors, so they just keep bouncing back and forth. And the structure of the atom that we're going to consider looks like the following. There is going to be a ground state, which we call, or this E to B bright transition is what we're going to call it. B is for bright. And the particle can move back and forth between these two states by absorption and emission of the photons that are inside this cavity. And that is characterized by this coupling rate G. And then also we're going to allow our atom to emit spontaneous photons specifically into free space at some rate gamma. And upon doing so, they travel to what's called a dark state. And we call that a dark state because now the particle will no longer interact with the light that's inside the cavity. The initial states of our atom in our light field are the following. The light is going to be prepared in what we call a coherent state alpha. This is a quantum mechanical state that's very well studied. It has a lot of similar properties to a typical light field, a laser field that we deal with in a classical sense usually. And the atom, we're going to specifically prepare in what's called a mixed state. And the mixed state will have populations, or will have probabilities to be in the bright state or the dark state. And by mixed, what I mean by that is that the atom will initially have some amount of entropy sitting within it. It's not moving, but it has entropy inside its internal degrees of freedom. And what we essentially want to do is track where that entropy goes and how this interaction affects the laser. Let's go ahead and check to see if the cavity field has changed first of all. In order to do so, we can work in what's called a phase space picture, where we can plot the cavity state at different times. And this plot here, it's essentially just looking at the probability of being somewhere in this phase space. This is the initial coherent state of the cavity. And you can see right here that it's got this blip over here on the right. And I put the circle here to show you that it's at some kind of radius. And also this angle phi as we go around the radius might be important. More specifically, the radius r corresponds to how many photons are in our cavity, and the angle phi will tell us about the phase coherence, essentially how coherent our state is as it interacts with the particle. So if this is the initial state, let's see what happens if it interacts with the atom weakly. So that means that the spontaneous photon will come out of the atom relatively quickly, and it won't interact on that bright transition so much with the cavity. What we find is that the distribution for the cavity state and the phase space looks basically the same as it did before it interacted at all. If you look closely enough, you see some changes, but this is already evidence that if the interaction is weak, there's really not so much of a change to the cavity state. If I instead look at the final cavity state, when the interaction is very strong, I find something very different. I see that my cavity state is still on a circle with, so that it still has a similar number of photons, but now the phase coherence has completely diffused over this entire circle. And by looking at this picture and this picture, you see, oh, look, the atom or the cavity state has certainly changed. So this is a nice representation to see that that actually can happen. We may not lose so many photons from the cavity, but the phase coherence of the state may change substantially. So I showed you pictorially now how different the initial and final cavity states are. Let's try to quantify that now. Can we assign a number to say how different they are? Right, can I assign something that says how distinguishable they are? If I gave you the two states in two different boxes and I tell you to tell me which one is which, would you be able to do so? In order to do that, we introduce the concept of fidelity of quantum states. And this is a generalization of the transition probability. And it works for not just regular wave vector states, but also for density matrices. This fidelity metric is bounded between 0 and 1, where it's equal to 1 if the two states are completely the same, and it's equal to 0 if the two states are completely distinguishable. Now, before I show you what the fidelity looks like, I want to introduce a couple important parameters. The first being n0, which is the average number of photons initially in the cavity, which is what we prepared. And then m is going to represent the strength of the interaction between the atom and the cavity. And if m is bigger than or equal to 1, we'll say that the interaction is weak. And if it's much less than 1, the interaction is strong. So here is my picture of the fidelity. On this vertical axis here, I have the n0, the average number of photons in the cavity initially. And then on this horizontal axis, you can just think of it as going from a weak interaction with the atom to a strong interaction with the atom. And what's plotted here is a so-called contour plot of the fidelity, where white colors mean that fidelity is close to 1 and the state hasn't changed much. And as it gets darker, it suggests that the state has changed substantially. And in particular, we see in the strong coupling, high photon case, the fidelity actually drops significantly and the states become very distinguishable. Another thing we might want to understand is the infinite photon limit. And what I mean by that is initializing the cavity with not 10 or 100 photons, but the limit as there are infinitely many. And the reason that's interesting is twofold. First, it's close to the regime of laser cooling, where the laser is super bright and there may be many, many photons, billions and more of photons in there. Secondly, it's interesting because you might think, since there are so many photons in the cavity now, how is it possibly going to change by its interaction with the atom? There's too many photons, maybe nothing happens. Well, we went ahead and calculated that too, and this is the result. And what we find, this is the infinite photon limit, where now I'm plotting the fidelity on the vertical axis, and we're going from weak to strong coupling as we move to the left. We see that if the interaction is weak, the fidelity still stays pretty close to 1. And as the interaction gets stronger and stronger, the fidelity still does drop, even though there are infinitely many photons. And as a matter of fact, in the infinitely strong limit, if I were to keep making this plot all the way for when m is going to 0, which means the atom and the cavity are interacting basically forever, then we would find the fidelity drops all the way to 0. So this shows that the cavity field can indeed be changed. Next, let's try to answer our second question. Can the cavity field remove entropy like the spontaneous photons do in laser cooling? And in order to answer that question, we can do another simulation and look at the entropy as a function of time of the 3 different degrees of freedom in our system, namely the atom, the laser field, the cavity field, and the spontaneous photon. And that's what this plot shows here. So let me point out the 3 interesting curves that are shown here. The first is the cavity entropy. Notice it starts at 0 because we started it in a pure coherent state, but then as time goes on, it gains some entropy. Now for the atom, of course, we initialize it with some entropy, right, by construction, and that gets removed in time as it interacts with the laser and the spontaneous photon. And lastly, we see that the spontaneous photon, well, it didn't exist at first, and now it's the entropy of the spontaneous photon goes up and up in time. So we kind of answered our question partly. The cavity does gain some entropy. And as a matter of fact, we can make measurements on that cavity and learn information about the initial atomic state. In that sense, we said the initial atomic state is imprinted on the cavity field. Now, you might be tempted to say that that means that the cavity field removed entropy from the atom. But as a matter of fact, we can't say that because the entropy of the spontaneous photon is always bigger than or equal to the entropy that remains in the cavity field. This is something that we actually rigorously prove. And what this means is essentially that the spontaneous photon knows everything that the cavity knew as well. So it's really more appropriate to say that the spontaneous photon is the real mechanism for entropy removal. The photon always removes the entropy, or more than the cavity can in all circumstances. So our summary here for the entropy project is that the cavity field can be altered if its interaction with the atom is strong enough. The entropy can be transferred, or some entropy can be transferred to the cavity field, but it also goes to the spontaneous photon. So we can't unequivocally say that the cavity field removed entropy from the particle. A possible extension of this work is to consider what happens if we were to pump this laser field in here with more photons in time, potentially allow for photons to leak out the side, and even allow for the particle to move around to get it closer to the true laser cooling scenario that we originally were thinking about with the proposition of this project. So that brings me to my conclusion. I showed you 3 protocols for laser cooling, trapping, and slowing, all of which have an emphasis on coherent control. And this resulted in a publication in New Journal of Physics back in 2018 in the experimental side. It also resulted in a theoretical publication in PRA the same year. Next, I showed you about the swap mott and how we can extend it to a trapping force. And this also resulted in a publication last year. And the adiabatic shortcut project also resulted in a publication a little less than 6 months ago now. And this last project, which had to do with the insight into the entropy transfer, is ongoing and will hopefully be submitted in the next few days, God willing. So with that, I'd like to thank you for your attention. I couldn't have done this with all the people listed here and a bunch of people more. So thank you again for your time, and I'm happy to take any questions.
Okay, thanks, John. Let's give him a virtual applause, I guess. However we do that these days. Okay, thanks everybody. Perhaps we could just open it. I don't know if there are any questions. You could put questions into the chat, or you could just unmute yourself and just ask.
Murray, maybe I'll have you moderate the questions. Is that okay?
Yeah. Obviously, the talk was completely clear and lucid, I think, John. That's the only conclusion here.
It looks like Luke has a question.
Yeah, go, Luke.
Hey, it's actually Tanya.
Oh, hi, Tanya.
Hey, John. That was really beautifully done. Thank you for that.
Thank you.
I have kind of a silly question. In like one of your last slides, I think it was 37, you showed the entropy of the cavity in the atom changing as a function of time. And the total entropy goes from 1 to like 2.25. And I know entropy always increases, but is there something a little deeper there for why it kind of goes up by a factor of 2?
Yeah, actually, there is a pretty satisfactory answer to that. And it has to do with the mutual information concept. And essentially what I mean by that is the spontaneous photon that comes out becomes entangled with the initial atomic state because it removes its entropy. And if I have a certain amount of initial entropy in my atom, let's call that S, then the mutual information between that initial atomic state and the spontaneous photon can be between anywhere between 0 and twice that initial entropy. So the fact that it's going up, maybe I think you might be seeing it's going up by a factor of maybe 1/2 or something here. I think that that's parameter specific, but there are explicit bounds you can place on just how much entropy that spontaneous photon will carry away from the system based on the entanglement with the atom.
Cool.
Does that answer your question?
Yeah, it totally does.
Thanks for the question.
Hi, John. So this is Bartolotta. I got a question about the like page 35. The kind of the interaction changes the state of the intracavity photons.
This page here.
Yes. So I was wondering, like in the strong interaction case, so can I like kind of understand this kind of, the diffusal of the phase as like because of the interaction between atoms and cavity photons, so like there becomes some number uncertainty that result in this diffusal, or like actually, like, what would you comment, like
Sure.
like
Yeah.
Understanding.
So in order to understand that question, I think it's important to remember that the way that we set up this system explicitly only allows any particular atom to absorb at most one photon from the cavity, right? Because as it absorbs that single photon, it will eventually spontaneously emit to that dark state and no longer interact with the cavity. So what that means is that the cavity can only change in photon number by about on the order of 1. And the plots that I show here have an initial intracavity photon number of about 100. So it only changed by about 1%. And that explains why the radius stays basically the same in the same place as in all 3 pictures. Now, the phase decoherence exactly can be understood by the fact that there are Rabi oscillations between each Fock state in the atom as it interacts with the system. And in the strong interaction case, these oscillations effectively happen many times before a spontaneous emission occurs, which scrambles the phase coherence of the cavity and leads this uniform phase distribution.
Gotcha. Sounds good. Thank you.
Does that answer your question?
Oh, yes. Cool.
Hi, John. Sorry.
Hi, Julia. Nice to see you.
Thanks. Yeah, nice to see you too. Great talk.
Thank you.
I wanted to ask a question about the adiabatic speed up. So you mentioned you chose a particular version. I was wondering if you could just explain a little bit how you chose that, or if there's an optimal one.
Yeah, I think that's a really good question. There are so many adiabatic speedup protocols out there that I'm almost tempted to say that we chose this one just to see what would happen, and it worked, so we rolled with it. But yeah, maybe I'll honestly leave it right there. I would be really interested to see what other speedup protocols would actually do. Sorry if that's not a satisfactory answer, but yeah, basically we wanted to try one out and just see if it could work at all.
Great, thanks.
Can I ask another question about the speed up?
Sure.
So in the slide that you showed about it, it looked like it kind of had time reversal symmetry. Could you maybe like say a few words about that? Does that make sense as a question?
Sure. Yeah. So time reversal symmetry is compatible with the fact that the speedup protocol was being applied in a situation where there was no spontaneous emission. So it's essentially just unitary dynamics. And so that just basically means if I flip t to minus t and apply the protocol backwards, I should in principle move back to my initial state. All the results that I showed had at most on the order of roughly 1 spontaneous photon. So it's still a relatively coherent dynamical situation.
But when are you not trying to, you're trying to only apply kicks in one direction or something, right?
That's right. So maybe a better answer to your question is the distinction between slowing and cooling. Slowing is something that is essentially just phase. I don't know if this. I'm not going to say the phase space. We can talk offline if you want a little bit more detail. But moving the atom's velocity around is not the same thing as compressing the velocity distribution. And slowing specifically has to do with moving it around. And that means we don't have to remove any entropy. And there really is no need for those spontaneous photons.
Okay, I think that makes sense. Thank you.
Yeah.
John, could I think that's a very interesting question, because, you basically, with your speed up protocol, you could go faster, but it would require more power, more intensity, right, of your control field. So perhaps, having time reversal symmetry is actually, somehow an optimum strategy, because it requires you to use, a smaller amount of power. Like if you have a constrained if you're constraining the total amount of power that you can supply, maybe that time reversal symmetry solution is the natural one that arises.
There are multiple time reversal there are multiple unitary processes that would give us the same beginning and end dynamics. So I don't think it's so simple as just considering whether or not it's coherent. But there probably is some theorem that says that coherent dynamics require less energy than those that involve dissipation.
Okay, are there any more questions? Okay, deathly silence. All right, yeah, I just wanted to say a big thank you to there are so many people who have come to this defense today, a lot of family and friends, at least I guess they're family, unless we have a lot of coincidental Bartolottas in the universe. But no, it's really great to see so many people, and I'm sure John really thanks everybody for their support. What we're going to do now is I think I'll just create a single break room, and I'll move the committee and John into the break room, and you can stay in this room. It's probably better to do it that way in case you disconnect or whatever. If you want to come back, you can come back into the main room. And I don't know how long we'll be there, but eventually I will throw John out and he can come back and talk to you all. So feel free to stay around here and chat and whatever. And we'll set up the second step of this. So let me
Right,
try.
see you guys
and
later. Wish me luck. Thank you so much.
We got Murray on.
Yeah, okay, finally made it round in this virtual world. Yeah, so John, I just congratulate you for a great PhD, well written, really nice research, a lot of independent projects, and it's been a joy, to supervise you for a few years. And I think everybody just will wish you the best for whatever the future brings, is how I would say. I would wish we had some bubbly. I don't know what we can do, but maybe in the future, right? Shouldn't be too long now.
I think Simon will help me out with that too.
Congratulations, Dr. Bartolotta. Well done.
Thank you.
Well done.
Yeah.
Well
Cheers.
Hey, John.
Cheers, everybody.
job.
Awesome. So proud of you, John.
Congratulations.
Congratulations, John.
Thanks.
Way to go, Johnny Bots.
Congratulations, John.
Thank you. Cheers, Jinx. Hold on, I'll be right back. I gotta cheers, Jinx.
There's a doctor in the family. Always move.
I think Jinx came prepared. That's what I've seen.
All right, it's time. Cheers, everybody.
All right.
Cheers.
Yay.
Yay.
Yay. Cheers, John. Woohoo. We'll celebrate at the wedding, and we'll celebrate the wedding and your PhD.
Yeah,
How's that?
Great. Yep.
It's a big year.
It's a big year, yeah.
Yes.
Here's a message from Danny.
What does it say? Congratulations, John.
Congrats.
Yep.
Well, how come I didn't get on?
What did everyone think? Were you guys able to follow it at all?
Completely.
Oh, Mary
The time
broke it
travel
down
part, I
for
got
us.
that part.
Does this apply to flux capacitors as well, or is that something else?
No, it's actually, if you think about it, the same exact thing.
Excellent. Thank you, John.
Welcome. Any other questions from the audience?
Wow.
No, just enjoy yourself tonight, relax, and spend some nice quality time with friends.
Oh, I will. Don't you worry. Thank you, Linda.
Good job, John.
Very nice. Proud of you.
Nice
Very
job,
proud.
John.
Yes.
Way to go, John.
Yeah, I wish we were all in person to celebrate.
We will
We
be.
will.
We will
We
be.
will.
Yeah, we will for your wedding.
Yep.
Yeah.
Yeah, it's coming up soon. It was supposed to happen in May, for those who don't know, but it got pushed to November.
Right.
Right.
Yeah.
I'm guessing that's part COVID and part PhD dissertation issues, right?
No, it's almost exclusively COVID, if you can believe it.
Oh, wow. Okay. Wow.
Yeah.
All right, John, we're signing off. Congratulations. We're so proud of you.
Congratulations.
Yes.
Thank you so much.
Good
Yep,
to see everyone.
congrats.
Awesome.
Nice to see everybody. It was wonderful.
Yes.
Bye,
Yes.
Likewise.
Linda.
Nice.
Love you.
Thank you for
Bye,
inviting
Rich.
us. Bye,
Bye.
everyone.
Your
Bye.
dad,
Bye, Deb. Bye, Michael.
your
Bye-bye.
dad,
Nice.
John,
Bye.
Dr. Bartolotta, your dad is very proud of you.
Oh,
Yeah.
yeah, I'm sure he would be.
Yes, he is.
Yes, he is. He's up there singing.
Oh, you don't hit leave?
You're gonna make me
He's
cry.
Oh, well, so we needed to say that. We love you. Take care.
Love you. Bye.
You too. Thanks for
Bye,
coming.
Ann. Nice, Mary.
Hi, John. Best luck with your new job in the summer.
Good job.
Oh, everyone froze.
Yeah.
Can you guys still hear me?
There he is. There he is.
Oh, I lost
Yeah.
you for a sec.
We hear you now.
So I'm gonna say congratulations, really well done. I'm gonna send you an email with some really minor comments on the manuscript. I think you're good. Like it's just a few typos here and there. Really clean thesis, well
Thanks,
written.
James.
It was really a pleasure to read. So thank you very much. Congratulations. Best of luck in the future. It's always fun to meet the family. Hello, family. It's great. Family support means a ton. It just really does. So thank you for being in John's life and helping him. So anyways, everyone have a great day. Congratulations, John.
Thank you.
Thank you, James.
Thank you.
Who's that? That's someone from Long Island over there.
Yeah, Maureen's still on.
Maureen, I think.
Yeah.
So John, congrats.
Hey, what's the matter with the
Thank
Long
you.
Island crew?
Yeah. So, it was so clear, and so hope you enjoy it and enjoy our time with your family. Yeah.
Oh,
See you later.
Opposite. Don't touch the screen. Boom.
go ahead.
I
Happy
Just
birthday.
I'm not on. Yeah, congratulations, John. I'm so
Thank
proud of
you.
you.
Nice to see you.
You're welcome. I'm glad you got through it all right. I would have been a nervous wreck.
Yeah, I was pretty nervous before, but once this started happening,
Yeah.
it became a lot more smooth.
Yeah,
You did a
you
good
did
job,
wonderful.
John.
You really did. Very nice.
Hey,
What's
Johnny,
next?
we sent you something in the mail. It should be coming. It was supposed to be there this afternoon, but something got messed up. So expect a package tomorrow.
Okay, thank you. Look at all these
You're
congratulations.
welcome.
I'm just looking at the chat
Congratulations.
now.
Love you.
Thanks, everybody. Thanks, Danny. Thanks, Liz. Everyone else too. I'm feeling very loved right now.
Well, you are.
As you should.
Definitely,
You are loved.
John, definitely.
You
Bye,
feel
everyone.
The love, you feel the
Bye.
hug? Bye, Jen. She
Congratulations.
froze up.
Thanks, Mo. Thanks for showing up.
Pete watched you, but he's not on camera.
Okay, no worries. Hey, how's it going, Pete?
He walked out of the room, but
that's
he
okay.
loved it. As much as we
Cool.
could understand, we loved it. You did a great job.
Yeah, I'm so happy you guys could make it.
Absolutely. Wouldn't miss it. All right. See you soon.
Bye.
Bye-bye.
Okay, I'm unmuting myself, John. I'm
Oh.
over here crying.
There she
I'm
is.
so proud of you. I'm crying. This is my son-in-law. I just want to say that to the whole world. I love you. You're a doctor. You're making me cry. I gotta go. I'm gonna hang up because I'm just crying.
I
I'm
love you too.
proud
I'll
of
talk
you.
to you soon.
I love you so much. I'm gonna go because I can't. I gotta drive now and cry. Goodbye.
Bye, Jackie.
Bye-bye now.
Whew. Oh,
How do you feel, John?
I feel pretty
Yeah,
relieved.
John.
I think I will feel extra relieved once I'm finally not looking at my computer screen. Not that I don't want to talk to everyone, but man, I've been staring at a computer a lot the last month.
Well, it shows, John. The work was very, very well done.
Thanks. Yeah, hopefully it was
great.
Yeah.
digestible. I tried to make it so people could follow as much as they could. Tried to use little equations and explain what I could in the time allotted.
Oh, that's perfect. I thought it was really, really well done. Good work.
Thanks.
Yeah, John,
Did
this
really good
introduction
job,
was
John.
amazing. I think really the introduction to the whole part with laser cooling trapping. I think that was so much improved from the last point. It was extremely good, close to perfect.
Yeah, I thought you would think so. I did a lot of work in the last 2 days.
I can imagine that you went through hell for the last few days.
Yeah, this is true.
A big change, actually. It was perfect. Perfect.
Thanks, Simone.
Yeah, congratulations, of course, and then I see you also later.
Yeah, sounds good. Yeah, you got. I'm feeling revitalized. You guys should come over.
Yeah, go take care of him.
I think we can manage that.
Good.
Yeah, it was a really, really good presentation, John. I imagine you are proud of yourself, but if you're not, you should be. It was really fun to watch. You did a great job.
Murray, did you record it too?
Yeah. I'll go through. I'll probably edit out some of the I'll have a look at the recording first, and then I don't know how we do this. Maybe I'll put it on LH for you, something like that.
Yeah, that works. Or like Google Drive, whatever works for you.
Right. My internet is pretty slow at my house, so it's often pretty hard to upload video files. So let me just work on it, and I'll send you an email.
Sounds good.
All right. Well, yeah, thanks for everybody and for everyone coming. I think I'm going to probably disappear at this point. I don't think that closes the session,
No, it won't.
as long as I do this right. But anyway, okay, we'll catch up, John.
Yeah, thanks, Murray.
Okay.
Thank you so much.
Hey.
Sign someone.